everyone, welcome to the course on computer-aided drug design. We will continue on the topic of docking. In the previous class, I talked about how to use AutoDock. Of course, there is another software called SwissDock also. So I do not have time to show that, but you can use that software as well. Okay. Okay. So let's go to this inflammatory pathway. So we have the arachidonic acid produced, which gets converted to prostaglandin H2 by the COX-1 and COX-2 enzymes. Okay, and the arachidonic acid also getting converted to the leukotrienes by the lipoxygenase enzyme. So there are drugs which are very specific towards the COX-2, okay, which are in the market like valdecoxib, rofecoxib, celecoxib. So we can download the structure of COX-2, okay, the crystal structure of COX-2 enzyme. It's called 1CX2. So if you look at your PDB, 1CX2, you can see cyclooxygenase 2, which is also called PG synthase 2. Okay, this is the one. It's there here. You can see this, and okay, it gives you the literature as well. Then okay, so this is the one. Okay, this is the enzyme cyclooxygenase 2, and there is the ligand in that. Okay, so a selective inhibitor SC558. Okay, SC558 is a selective inhibitor of the cyclooxygenase 2. Okay, now then we can use the software like AutoDock. We know the active site of this particular enzyme, where these are the amino acids present in the active site. So when we do binding of each one of these molecules, okay, there are about almost 12 molecules which we have selected, which are known to have selective, and some of them are not so selective, but we know the activity of them, that is IC50. So we get the binding energy or interaction energies using AutoDock for these 12 of these molecules, and here we plot their activity. Okay, as you can see here, and we see there is a very good negative correlation. So as the binding energy increases, the activity also increases. Okay, so this is quite good correlation coefficient. So what's the use of this? Suppose we have another molecule which we think we can design, which may be better active. We can bind it to this COX-2 enzyme, and we can see where the binding energy or interaction energy comes, and then we can sort of predict its IC50, whether if it comes here, and so on actually. Okay, so this can be used as a nice predictive tool. Okay, now let's look at another example. The platelet aggregation. Platelet aggregation is a very serious issue which leads to thrombosis. Okay, platelet inhibition. Endothelium prevents platelet and plasma coagulation factors from meeting the highly thrombogenic subendothelial extracellular matrix. Okay, so non-activated platelets do not adhere to the endothelium. Okay, so activated platelets adhere. Okay, that's the big problem. There are many drugs which are given for antiplatelet aggregation. Nowadays, aspirin is seen to be known, sodium salicylate, dihydroxybenzoic acid, clopidogrel, okay, and so on. Actually, a lot of substituted phenyl systems and all are there. So, antiplatelet activity of many of these drugs have been reported in literature. We also have looked at some compounds like this. They are called Tianol. Okay, you can look at it. It's almost like aspirin. R1 and R2. We can put a lot of substitutions here, so we can get a huge number of derivatives. We can look at antiplatelet activity of these, and COX-1 is the enzyme which is known to be involved in the platelet aggregation. As you can look at the pathway here, here comes the cyclooxygenase. Okay, so COX-1 we need to inhibit. So again, if you look at the PDB, very nice 3D structure available of COX, COX1. So we can take that, and then yeah, we can, as you can see, there are many COX1s here. Many COX1s. This is the COX1. It's complex with the Morphi-Zolac. This is another COX1. Okay, mutant COX in fluorbiprofen. There are many COX1s there in the literature. Okay, we can download based on unoccupied. Okay, so based on our requirement. Okay. Based on our requirement, we can download the crystal structure from PDB, and of course we can use your Autodoc, and we have a large number of molecules which we have synthesized in all derivatives. Okay, so we can bind all of them or dock all of them, as you can see here, docking to the COX1. Okay, docking to the COX1 here. This is the cyclooxygenase 1. Large number of molecules docking to that, so we can get a relationship between the binding energy or interaction energy, as we call it, or energy difference between docked and undocked. And then this is your percentage inhibition of platelet aggregation. Again, we see a nice negative correlation. Okay, as the binding or interaction increases, the activity or percentage inhibition also increases. So we can use this type of target-based design also for designing new molecules. So new molecule, if I come up with a new structure, I can dock it to the same enzyme, and then based on the docking energy or binding energy or interaction energy, I can predict what will be its activity. Okay. Okay. Let's look at another example, antihypertensive drugs. These drugs are used widely for reducing your blood pressure. Okay, there are certain beta adrenergic receptors. Okay, there are some angiotensin 2 receptors. Okay, angiotensin converting enzyme inhibitors. Of course, diuretics. Generally, these are very popular. Of course, doctor also prescribe diuretics as well. So look at this beta adrenergic antagonist. Okay, there are two, beta 1 and beta 2. Okay, so there are non-selective drugs. They are called beta blockers, which may bind to both beta 1 and beta 2, or they are selective ones. That is non-selective. Catilol, pindolol, carvedilol, propranolol, and there are beta 1 selective also. Acebutolol, atenolol, betoxolol, and so on actually. Okay, there are non-selective beta 1 and beta 2, or there are selective beta 1. Okay, so as you can see, synaptic sympathetic nerve comes in here. Okay, and then which goes here, and then we have the cardiac myocytes. So it basically blocks the beta 1, or it blocks both beta 1 and beta 2. Okay. So again, there are structures available which okay, beta blocker, as you can see here. Okay, there are many beta blockers, a lot of beta blockers. Okay, as you can see, almost 25 of them are there. Okay, beta blocker. We have the drug propranolol bound to that. Okay, so a lot of drugs are there, a lot of drugs. Very nice 3D structure available of COX. Drug called propranolol bound to the beta blocker. Okay, and so once we dock all these drugs to the active site of, and then we plot the IC50, PIC50, which got from literature, and then this we call it the intermolecular energy or binding energy or interaction energy. Again, we see a nice correlation, more negative Okay, better is the activity, less negative, less is the activity. So very nice. Okay, then again involved in the hypertension, there is another enzyme called angiotensin converting enzyme. Okay, so these ACE inhibitors produce vasodilation. Okay, so what happens is we have this enzyme, ACE enzyme, which converts A1 to A2. Okay, which leads to vasoconstriction, increased blood volume, all these things. Okay, so A1 is called angiotensin 1, which leads to angiotensin 2 by this enzyme ACE, angiotensin converting enzyme. So there are drugs which block this particular enzyme ACE, and so A1 doesn't get converted to A2. Okay, so the vasoconstriction doesn't happen. Okay, so this is how these drugs work. They are called ACE inhibitors. Okay, there are a lot of drugs. Benzapril, captopril, enalapril, fosinopril, lisinopril, ramipril, and so on. So all these drugs work towards blocking this particular enzyme called ACE. Okay, angiotensin converting enzyme. Okay. Again, there are many ACE. Just type ACE. So as you can see, there are many crystal structures of ACE here. There are many crystal structures of ACE here. So you can be more selective towards what you want to have. Okay, as you can see. Okay, what you want to have. Angiotensin converting enzyme in complex with lisinopril. This is the drug which is binding to this particular enzyme. Okay. You can see the lisinopril maybe here. Yeah, you can see the drug here. Okay. Okay, so we can easily download the structure of the protein, and then we can dock all these various ACE inhibitors, and there is literature data on the activity of these drugs towards the ACE percentage inhibition. So you can see this docked in ACE. Okay, this is the drug docked in ACE. Okay, so as you can see here, this is the binding energy. More the binding, higher is the activity. This is the activity on this axis. So a lot of ligands, and these triangles are the drugs here. And okay, so you get a nice, reasonably good straight line with R square of 0.7, which is not bad. So as the binding energy increases, the activity also increases. So if you are trying to design a new molecule for ACE inhibition to prevent the angiotensin 1 getting converted to angiotensin 2, all you have to do is design and start docking each one of them and see where their binding energy comes, and from there you will be able to predict what could be its activity. And all these data is obtained from literature. So from the literature data you get this graph, and then when you start designing new molecules, we can use this graph for predicting the activity of new compounds. So that's the beauty of target-based drug design. Okay, so another example we will look at, this is tubulin. Tubulin assembles and disassembles to form microtubules. Okay, microtubules undergo continual assembly and disassembly within the cell. They determine the cell shape in a variety of cell movements. Okay, cell locomotion, intracellular transport of organelles, separation of chromosomes during mitosis. Okay, so there are drugs which prevent the assembly, there are drugs which prevent the disassembly. Okay, vinblastine, vincristin, these are drugs that inhibit microtubule polymerization. Okay, so it does not allow the assembly. Whereas taxol, paclitaxel, that drug binds to and stabilizes the microtubule. Okay, so it prevents the disassembly. So taxol is used in breast cancer, ovarian cancer, lung cancer. Okay, so you assemble, disassemble to form these microtubules. So there are drugs which prevent the assembly. There are drugs which prevent the disassembly also. Okay. Okay. So as you can see, Taxol binding to certain mutated tubulins is taken from this particular reference book. Okay, so this is we have the active site shown in this picture. Taxol binding into the active site. Okay, the red ones are oxygens, blues are nitrogen, green are carbon, and whites are hydrogen. Okay, so we have several molecules binding to the particular protein, and again you can see we call it decrease in energy or increase in the binding and a negative more binding activity, so the activity keeps increasing, and as it becomes more better binding, more interaction, more decrease in the after binding, the activity value also keeps increasing. So I am showing a lot of examples of target based drug design where we can okay, do the binding of various ligands. Once we have the protein of our interest can be obtained from your PDB database bank, okay, and then we can perform the docking, and I showed you in the previous class how to do the docking. Of course, there is AutoDock is a very good software, and also the Swiss dock is also there, which can also do a good job. It is done through a web server, and all the software is belonging to, yeah, so we can do the docking here also. We can submit the docking. I don't want to spend too much time, so here we give the target, say we can give BB99, or yeah, so we have this particular protein, and then here the other place we can put the ligand, and then we can submit for docking. Okay, successfully set up, and then here we can put our ligand, okay, ligand name, okay, so we can load the ligand, and okay, so we have loaded both a aspirin mol2 file, 3v99 is a Philox file, and then we can give the job name, aspirin dash Philox, and then we can give my email ID here, and then the results will come to you. Okay, results will come to you. Okay, start talking. Results will come to you. Okay, the results from SwissDoc comes to your email. Okay, like this. Okay, if you click on the results, as you can see here, you can see the binding energies between aspirin and Philox. In fact, that's what we gave, the 3v99 and aspirin. We gave aspirin in mol2 format, 3v99 as a PDB. So we can see this, and here you can see that the estimated delta G, this gives the highest negative binding energy. This is all the cluster 0, okay, and then cluster 1, cluster 2, and so on actually. So you can see here, we can click on different clusters. Okay, so we can see the aspirin here, as you can you see the aspirin here? Aspirin is seen here. Okay, the aspirin is here, yeah, somewhere here. Are you able to see the aspirin there? Yeah, you can see the aspirin here, and this is the Phylox enzyme. Okay, this is the output from the Swiss doc. So it gives you large number of results and different clusters also it gives you. So you can see how the aspirin binds. Okay, you can look at different clusters and okay, so aspirin has come down there. So in different locations, starting locations, and then it binds. Okay, you can see the aspirin here. Okay, so we can download some of these prediction files. We can look at them in more detail, which I have downloaded. Okay, so we can look at okay, so this how the aspirin various clusters. So generally this cluster seem to be the highest. That must be cluster 0 and cluster 1. Okay, so predominantly aspirin seems to be binding in these places more than any other places. Okay, so this is the aspirin as you can see here. Okay, so the other cluster is cluster 1. Okay, where aspirin is bound more. Yeah, here. So cluster 0 and cluster 1 is seen here. So predominantly cluster 1, cluster 0 and cluster 1, we can view them. Okay, so SwissDoc is another interesting program which can be used for docking ligands to protein, and it gives you then the estimated delta G in kilocalories per mole. Okay, there are other softwares which are also which looks at the binding site analysis. Suppose you have many proteins and you are interested to know what is the relationship between those protein active sites. There are some softwares. Okay, and there is a software called PatchDoc, and there is another software called MultiBind. PatchDoc is molecular docking algorithm based on shape complementarity principles. So I can put a protein and then I can put a ligand, and if we try to find what is the shape complementarity. So I can take the same ligand as a probe, and then I can look at different proteins. That's called PatchDoc. Okay. Another software called MultiBind. So it aligns multiple alignments of protein binding sites and then recognizes spatial relationship or common binding patterns of set of proteins. Okay, so that's called MultiBind. Okay, MultiBind looks at different proteins. Okay, and then or we can we can upload it as a zip file. So it compares different proteins, okay, and it will find out common chemical patterns. Okay, the results of MultiBind again comes to your email ID as seen here. We can click on that, and basically MultiBind looks at basically compares different proteins. Okay, it compares different proteins and see what are the common features, okay, in their active sites. This is very useful if you are looking at families of protein. And basically in the example we looked at the 3V99 We looked at 3V99 and we looked at 5KIR. 3V99 is 3V99 is 5-lipoxygenase protein with the arachidonic acid bound to it, and 5KR is cyclooxygenase 2 enzyme with the Vioxx bound to it. Cyclooxygenase 2 is involved in prostaglandins, and 5-lipoxygenase is involved in leukotrienes. Okay, so you get a result like this. Okay, so the two proteins 3V99, okay, which is the 5-lipoxygenase protein, and the other one is 5KR, which is a cyclooxygenase protein. It has Vioxx bound to it, and 3V99 has arachidonic. So these two protein active sites are being compared, hydrogen bond donors, aliphatic, acceptors is there, donor is there, okay, and you get a score of about, it gives you a score as well, score of 10.0, which is low, okay. Higher the score, that means higher is their comparison, whereas lower the score, lower is the value, okay. So this software is useful if you are looking at comparing different active sites of protein. This is useful, yeah, this is useful if you are going to have a comparison of different proteins and see whether same drug may be acting on these active sites of these two proteins, okay, because they may have similarity in their active site structural features. For example, there are some proteins in the arachidonic acid pathway, in the prostaglandin called PGFS, PGIS, PGDS, just like PGES. So you can compare proteins. Then it says there are some common features: PGFS versus PGIS, PGDS versus PGFS, PGES versus PGIS, PGES versus PGFS. So it can give some sort of a score and say these are the common features between this protein. Okay. Yeah. So these are these PGES, PGDS, PGIS. Okay. So what is the common feature between these proteins? So we can use the software called multi-bind, and then the software may give results like this. Okay. Right. Commonality between these proteins. So pairwise comparison, and then say gives a score. So these two proteins, PGFS and PGIS, have a common score. What is that PGIS, PGFS? Like I mentioned here, they all come in the arachidonic acid pathway. Okay. Okay. So we have this PGIS, PGDS, PGIS, PGES, PGDS, and so on. So these are what are the commonality between all these proteins? That's what this particular software will be able to tell. Multi-bind. If you look at the other one, the patch dog, what it does is it takes a molecule like a ligand, and then it takes it as a probe and see what is the shape similarity between that ligand and the particular molecule of interest. Or a protein interest. Okay, so it will tell you shape complementarity criteria. It's based on that. That's called the patch dock. Okay, so this software is also very, very useful. So it doesn't do a docking. So it gives you a receptor protein molecule, it gives you a ligand molecule, you give the email address, and then it does the job. 3B9, sorry. So we can give this. So we can give a choose file here. We can again give a choose file here for your ligand, and then we give the email address. Okay, and then it does the job here. So it gives, basically looks at the shape complementarity between the ligand and the protein. Okay, so the receptor molecule we can choose from our file 3B99. We have been looking at it for a long time. Okay, PDB 3B99. So we can give a PDB chain ID example here or upload file. So we can say 3B99, and then here we can ligand molecule. We can give our aspirin, as you all know. Okay, aspirin mol2 file is accepted here. I think mol2. Then I give my email ID. Choose complex type default enzyme submit form. Okay, so that's how it is done. So the results of PatchDoc, which is a software that compares the structural features of the ligand and the protein. That means basically whether it's got concave regions and convex regions, and try whether they have a complementary regions, and predict whether the ligand will go and bind to that protein. That is given by PatchDoc, and the results again come to your email. And as you can see here, we were looking at the aspirin, and we were looking at the 5-lipoxygenase protein 3B99. So it tries to see and try to give a score, okay, big score, small score, and so on actually. So PatchDoc and that sort of comparison of a ligand like aspirin in this particular case, and protein 3B99, that's a 5-lipoxygenase. So PatchDoc can be used for molecular docking. So it sees whether there is a convex patch, concave patch, and whether there is a complementing convex and concave patch in the ligand. So we can say possibly they could be interacting at that places. So it could be protein ligand, it could be two proteins, it could be drug, protein, DNA, so many things we can do that actually. So it's just based on shape complementarity criteria. So if you have a concave and if the another ligand has a convex and the matching, so we can say there could be a interaction or binding here. So this sort of gives you the score on that actually. Okay, so this is another software which is useful when you are looking at ligands and proteins. It will be sent to this particular email. So this is also a very useful software. Okay, so this multi-bind looks at several protein binding sites, and then it says what is the similarity principles like hydrophobic, hydrophilic, polar, non-polar, and so on. Whereas the PatchDoc looks at a ligand and a target protein and see what is the commonality based on their shape. Okay, as you can see, they are all web server based. So we upload our problem and the results will come to your email ID and we can start analyzing them. So they are all free of charge. Okay, So we will continue more on the topic of computer-aided drug design in the next class as well. Thank you very much for your time.